Kia ora, everybody. Welcome to the webinar today. My name is Tim. I'll be your host. I'm a member of the EGP committee. This presentation will look at the history and nuances of C2 capacities for post-installed anchors in concrete within a New Zealand context. It can be a hard topic to dive into without significant time investment, and this presentation will hopefully provide an overview that will help engineers understand what the values they use in design are actually representing. The topics covered will include what does a C2 capacity actually represent, the history and evolution of C2 testing protocols, common areas of ambiguity and misinterpretation, and application of C2 values in accordance with NZS 3101. Our presenter is Robert Hudson. Robert's the engineering manager of Python Fixings based in Seattle, specializing in the seismic assessment and strengthening of existing structures. Robert manages research, development, codes and approval for Python across Australasia and North America. With his involvement in the development of ICC acceptance criteria, testing of post-installed anchors to ETAG 001, testing of such anchors, and Board of Directors position on the Concrete and Masonry Anchor Manufacturers Association of North America, Robert is able to provide particular insight on this topic. Now, as Megan said, if you have any questions, type them in the chat area and we will endeavour to answer as many as we can after the presentation. Please welcome Robert. Robert, it's all yours.
Thank you for that, Tim. Much appreciated. So I guess to start off a little bit about why we're running this in the first place. There is definitely, without a doubt, a little bit of frustration in the industry around the use of C2 capacities for anchors in concrete. The messaging we hear, statements along the lines of why these capacities so damn low, and it is a very understandable frustration. In addition to this, there is without a doubt a spectrum of understanding behind what these capacities actually represent in the industry. I vividly remember being a grad at Becker when I came out of university and designing using C2 capacities. And if I'm being honest, if someone had asked me at the time why I was using a C2 capacity, my answer would have been something along the lines of because it is the seismic capacity of an anchor in cracked concrete. And that would have been about the limit of my understanding. But there is actually a lot more that goes into these capacities, and they do represent something quite specific. The idea behind this presentation is to kind of give a little bit more detail into what they are representing and what they're not representing, as well as some of the background on how we got here and some of the things to watch out for in design. It is very focused towards the level of knowledge that I think will be useful for designers when using these capacities, so that you are aware and able to account for some of the nuances of these values, because then it's not a magic number, right? The second we think about it for more than a couple of minutes, we realize that one number can't possibly represent the actual capacity of an anchor in all the scenarios we use them in. There are some proxies that are in place. And so we'll see if we can give everyone a bit more of an understanding so that when you're doing your designs, you can kind of understand what's going on really specifically with your anchors and account for them accordingly. I've really split the presentation into three sections. The first is a little bit about how we got here, kind of what's the background, what's going on in the world at large in this kind of context. The second part will go into the weeds a little bit on what tests are actually done on these anchors in order to, in order for a manufacturer to publish a C2 capacity. And then the last section is on highlighting some of the ambiguities and areas where really these capacities might not line up very well with what we're doing, so that as a designer, you're aware of them and can kind of account for them appropriately, just using good design practices. I probably have about 45 minutes, and so we should have questions, plenty of time for questions at the end, and I believe there's a chat function that people can use throughout the presentation. Okay, how we got here. So these are images from the 1994 Northridge earthquake in California. Actually a very large earthquake. So the PGA in the highest acceleration area was about 1.8 G. which when we compare it to what Christchurch was, which is about 1G, pretty drastic kind of event. But believe it or not, prior to this, the industry was using monotonic capacities in uncracked concrete to design post-installed anchors in concrete, which I suspect we can all intuit isn't going to be appropriate for a lot of the design that we're doing for post-installed anchors in seismic regions in concrete. And as a result, there was pretty widespread failures of anchors, among many other things, which is to some degree understandable in an event this size. But the anchors was really a highlight, or at least one of the highlights that came out of this earthquake in terms of learnings. So much so that actually the US banned post-installed anchors completely in seismic applications for the best part of 2 years. And this is kind of a timeline of what we have seen since then. So the industry, especially in the US, primarily led this effort, but there was a bit of an effort to put together a method for seismically rating post-installed anchors in concrete, basically looking at how concrete behaves, which is kind of the cracking mechanisms of concrete, and the seismic actions we expect and allow for on anchors in a seismic event. The first codified method for this didn't actually get implemented until 2001, and this was done through the US Concrete Code, specifically ACI 355. Interestingly, they didn't invent this method. The Canadian nuclear industry had actually already been using it for post-installed anchors in their nuclear facilities, which they deemed at the time, probably quite responsibly, that they should have a higher level of redundancy for post-installed anchors in these contexts. And so that was adopted into the American Concrete Code. Then in 2013, the Europeans came to the party and developed what most of us in New Zealand are most familiar with, which is kind of the C1 and C2 tiered rating system for post-installed anchors. A quick note on the kind of code terminology. In 2016, the Europeans did slightly restructure how they publish their codes. And so while we're often familiar with the reference to ETAG 001 Annex E, this actually isn't quite the right reference anymore. They just kind of restructured how they do their codes. The content didn't meaningfully change. And then 2017 is when we came to the party, and we will almost certainly, everyone on this call will be very familiar with this. We start referencing the Eurocode documents and in effect start using C2 capacities all over the country. What I think is really interesting about this, but I am a bit of an anchor nerd at this point, this really isn't a static part of our industry. This really is still developing across the world. And the US, the ACI 355 committee has actually already approved, and it's going through the process of getting implemented into the next code. Pretty serious changes to ACI 355. They are completely removing what we consider as C1 and will be implementing C2 as the appropriate capacity to use for any anchor in a seismic zone in the US. And so they will not even have the kind of tiered system that Europe has. They will just have kind of the non-seismic zone and C2 capacities. And so this really is, definitely seems to be more and more the way that the world is moving in terms of post-installed anchor design. Now, in terms of what we're doing in New Zealand, many of you will have seen and read this a number of times. All of this comes from one sentence in 3.101, which is kind of amusing. But we have there post-installed mechanical anchors and post-installed adhesive anchors shall pass the pre-qualification testing stipulated in ETAG 001 Annex E and be designed in accordance with EOTA Technical Report 045. As I mentioned before, technically, both of these references are actually out of date. The significance of this in terms of content is pretty negligible, but I do highlight it here just to note so that if you see it in suppliers documentation, the ones down the bottom are the appropriate codes really to be referencing, and the actual content difference is fairly negligible, but you would be expecting to see on supplier documentation reference to Technical Report 049 instead of ETAG 001. And Eurocode 2 for the design. In terms of kind of why we have such a focus on kind of C2 and rather than C1 in New Zealand, this is the document out of Eurocode, or sorry, the table out of Eurocode that defines what capacity you should be using for an anchor. It's basically just a function of seismicity and importance class. The importance classes in the Eurocode do align pretty well with what we have in 1170 in New Zealand. And so for the most part, you can just take them as a direct comparison. The seismicity does take a little bit of effort to compare them properly. There was a paper a couple of years ago, or maybe more recently, that was published doing an example calculation. It does give you slightly different results if you compare it directly to 1170. But as a general rule, for the vast majority of what we're doing in New Zealand, we have a seismicity greater than 0.1 G. And unless you're dealing with a importance class or importance level building 1, or you're dealing with a shack at the very top of the North Island, you're almost certainly going to be required, following our code, to be using C2 capacities. And that's kind of the situation we're in, and why this is really front of mind for so many engineers in New Zealand. Okay, so that's a little bit about how we got to where we got to. The next section here, I'm going to do a bit of a dive into the testing that we do, or any supplier does, to actually provide a C2 capacity, and kind of some of the background as to why the testing is the way it is. I'm not going to go into, the intent here isn't for you to be able to go away and do the testing, right? The intent here is I'm concentrating on the things that are relevant to be aware of and to think about when you're designing such anchors, so you can make appropriate considerations where it's relevant. Now, taking a step back for just a second, there's two things we really care about with anchors in seismic scenarios or seismic locations in concrete. We care about the actions on the anchor, so that's just kind of the cyclic tension and cyclic shear behavior. And then there's also the behavior of the concrete, and more explicitly, the cracking behavior of the concrete. Quite intuitively, if we start having cracks in our concrete and our anchors are in those cracks, that's obviously going to impact the performance of any post-installed anchor. Take the extreme case where your crack starts becoming wider than your anchor is going to fall out of the hole. Thankfully, we don't often have that scenario, but it's a spectrum, right? And the larger the crack, the more impact we have. But there is this baseline assumption when we talk about this, that we are allowing for, when cracking occurs in concrete, that crack will occur where that anchor is. And this wasn't just good judgment. This was actually based on a research program that was done in California in the 2000s. I've got a screenshot for one of the test results there. The idea behind this, and it was one of the test programs that was trying to build the data that was required to build these test programs for anchors. But what that was looking at is what is the probability that when we get cracking occurring in concrete, that crack occurs where our post-installed anchors are. And the key takeaway is that it's very, very likely, much above random. And this makes a lot of sense. We have a very homogeneous, or reasonably homogeneous material. If we put an anchor into it, it acts as a stress raise. And then when we start getting cracking occurring in these concrete units, which we do even under just surface loads, right, but definitely under kind of design level loading, because we have a stress raise there, there's a very, very good chance that crack occurs where the anchor is. And so the baseline assumption is that if we're putting an anchor into concrete or reinforced concrete, we are assuming that when cracking occurs, that cracking is going to happen where that anchor is. And that's a pretty reasonable assumption in my mind. The other thing we care about with regards to cracking is the size, right? The larger it's going to be, the more of an adverse reaction it's going to have, or adverse impact it's going to have on our post-installed anchor connections. Now, there are two numbers to be aware of, and I suspect you're all going to be sick of me saying these numbers by the end of the webinar, but there is a 0.5 mil crack width and a 0.8 mil crack width. The 0.5 mil crack width is very roughly intended to represent kind of service conditions and moderate seismic events, and this is the crack width that a C1 capacity is allowing for. And then we have that slightly larger one, which is a 0.8 mil crack width, and this is what a C2 capacity is allowing for. That 0.8 mil crack width is intended to represent basically the scenario where you have a reinforced concrete beam. If you come just outside of the plastic hinge zone, and then you load that minimally reinforced concrete beam to the point where you just start getting yielding in the tension reinforcement. The 0.8 mils is a prediction of the crack width at that point in that scenario. So when you're just getting yielding of your reinforcing in your concrete beams. That's what it's trying to represent. And that's what we use in a C2 test. Quick note, as everyone really should be aware, there is really no test program or way for anyone to rate post-installed anchors in plastic hinge zones. The damage and cracking we expect in a plastic hinge zone in a seismic event is pretty dramatic, and nobody's providing you a capacity for that. As a general rule, if you're wanting an anchor to perform in a seismic event, you really probably just shouldn't be using post-installed, or definitely shouldn't be using post-installed anchors in plastic hinge zones. Okay, the test program. So this is a snip from the European documents on the tests you need to run to rate a post-installed anchor in concrete. The ones of relevance for us are the ones on the right-hand side in red. You can see the C1 tests for producing a C1 capacity, and the ones on the bottom right are all the tests that you have to run for kind of C2 capacities. There is actually a whole range of other really interesting tests in here, which might be of interest. So you have these tension tests. If you can kind of see my mouse on the screen, you are actually allowing for, in general, things like variability of drill bit diameter, right? The impact that the slight changes in pilot hole has on anchor performance. Things like over torquing, under torquing of different types of anchors. And so there is a little bit of extra stuff that goes into the test program. But what we're really going to concentrate on in this talk is the stuff on the right, which is the C1 and primarily the C2 tests. And these tests can basically be boiled down to trying to allow for and quantify the impact of these three mechanisms. The first two, and you all get an insight into my lovely graphic animation talents. The first one we care about is the impact of cyclic shear. This is quite intuitive. If you have a reinforced concrete frame, a steel moment frame, and you've connected it for in-plane strengthening, say, to a reinforced concrete structure, you're going to get cyclic shear behavior in your anchors. The next one is cyclic tension in the anchor. This is also quite intuitive. If you've connected Strombacks or some such connection, you're going to get cyclic tension behavior in that anchor. And these are the two mechanisms that a C1 capacity is allowing for. So when we do C1 testing, we're allowing for these two mechanisms, and we're allowing for crack widths up to 0.5 mils. What a C2 capacity additionally allows for is this last mechanism, which is cyclic crack behavior in the concrete. And there's a number of scenarios where this occurs, but the one that is really clear is if we think about a reinforced concrete moment frame, we think about that beam. If we put that reinforced concrete moment frame into a seismic event, we are going to get moment reversal in the reinforced concrete beam, which means our cracks are both going to open and close. Because we have this baseline assumption that our anchor is in the crack, that means these cracks are going to open and close around our anchors. And this obviously is going to have an impact on how the anchor behaves. And so what a C2 capacity is trying to represent is the impact of these three mechanisms and a crack width up to 0.8 mils wide. Now, one thing that I do want to kind of highlight here, because it gets misunderstood, I think, quite often, we often see that we have a tiered system with kind of non-seismic capacities, kind of C1 capacities and C2 capacities, and we assume it's just a scaled method. It's kind of intuitive, perhaps, to think that we might just have a larger strength reduction factor that's used to generate a C2 capacity rather than a C1 capacity, but that's not really what's going on. The difference isn't in the reduction factor that we're using. The difference is the additional mechanism that we're allowing for, which is the cyclic crack width, and the slightly larger width of crack that we're allowing for. Those two things are really the difference between a C1 capacity and a C2 capacity. Now, I apologize to anyone who's run this testing, because I'm going to oversimplify this a little bit. The test procedure is the most complex post-installed anchor test procedure I am aware of. But it basically boils down, when you're trying to calculate a C2 tension capacity, basically boils down to this formula. oversimplistically, but basically it does. What we have on the left there is the C2 tension capacity. We have these two reduction factors, alpha and beta, and then we have this baseline capacity that we start with. And so for the tension capacity, we're going to kind of go through how we, where each of these values come from. So our baseline is just the monotonic tension capacity of an anchor in a crack. It's actually using the 0.5 mil crack, which is that kind of moderate seismicity, serviceability kind of baseline performance of an anchor in a crack. And then we have this alpha and beta reduction factor that we apply. Now, the alpha factor, what that is trying to represent is the loss in load carrying capacity from each of the mechanisms that I showed before. Your cyclic tension loading on the anchor, the additional wide 0.8 mil crack width, and the cyclic crack behavior around the anchor. The formula for C1, by the way, is exactly the same. It's just accounting for less mechanisms. And so we have a couple of tests we do. We have this monotonic test in the slightly larger crack width that's investigating what the additional crack width impact is. And then we do a cyclic tension test on the anchor in a crack, and we have the cyclic crack test. Now, one thing to highlight here is that we don't actually superimpose the impact of the cyclic tension test and cyclic crack test. This is quite good because otherwise the capacities would be even lower. But this was based on a really nice piece of research that was done, again, same kind of time in California. All of this really comes out of there, or the University of Stuttgart. And what they did is they built a reinforced concrete frame. They put a simulated non-structural element underneath the reinforced concrete beam. They put it through thousands of cycles, and they measured across time the tension in the anchors and the crack widths. And basically what they found is that the maximum of each don't occur at the same time. And so when we're generating these capacities, we're actually just, when we talk about tension, we actually just account for whichever one has the most adverse impact. More excellent graphics. Now, in terms of what these tests actually look like, the one on the left, again, is that cyclic tension test where we're just loading the anchor cyclically. That dotted line is crack width. So we kind of start at a smaller crack width. We start with a lower cyclic load, and then we increase the crack width to that full 0.8 mils, and we bring the load all the way up. And then that graph kind of reverses when we look at the cyclic crack test. We basically have constant tension load, which increases throughout the test. And then we cyclically open and close that crack around the anchor. You start with really small widths, and you work your way all the way up to multiple cycles of a 0.8 mil wide crack. Now, there we go. I got some arrows. Now, to give you a bit of a kind of sense of scale of the impacts of these two tests, this will vary quite significantly depending on the type of anchor you're using. Some anchors are quite resilient to some of these mechanisms, others are less resilient. But it would not be unusual to expect a kind of reduction factor from the cyclic tension test, kind of in the range of kind of about 0.9, so maybe a 10% reduction in capacity. And the kind of reduction factors that I might expect if I was testing an anchor and putting it through the cyclic crack test would be in the range of kind of 0.2 to 0.3, which is 70 to 80% reduction in anchor capacity. Overwhelmingly, the reason that our C2 capacities are so much lower than what we used to use is because of the cyclic crack test. And this is the test that kind of C1 doesn't take into account, which is why C1 capacities are significantly higher. Now, when we were doing this testing, we started playing around in our own lab with some of the variables. We wanted to understand kind of what the sensitivity of these variables were, because you'd get some test programs where your variable is set as a number and you could increase it and decrease it, and it's not that sensitive and it doesn't really have a big impact on the outcome. So we wanted to understand the kind of how sensitive these variables were to the end result we were getting. And so we played around with it a little bit, and the conclusion was they're incredibly sensitive. And the two variables that we care about here are the crack width, so that 0.8 mils, and the number of cycles that we're putting the crack cycle test through. If you have a crack width that's a little bit more, than 0.8 mils, you get a significant reduction in capacity. If it's a little bit less than 0.8 mils, you get a significant increase in capacity. And similarly for the number of cycles, especially at maximum crack width, if you add more cycles to that test, your capacity drops. And if you reduce the number of cycles, your anchor capacity increases significantly. And this will be important for something I'll mention later in the presentation. But these values, where they sit, really is what is defining our C2 capacities. And especially, it's really this test. Just quickly on the beta factor, what this is doing is accounting for displacement performance of anchors. It doesn't, in my experience, really have a big impact on the end result in terms of the capacity. Might have a little bit, but not a big reduction. But what it does do is it has pass-fail requirements. And so it's making sure the two things it cares about basically is the spread of displacements across multiple tests. And so what you're protecting against there is a unpredictable displacement performance of anchors, which is not something we want. And it also has a maximum displacement of 7 mils in the test. And so if you have any anchor that is displacing unreasonably far in these test programs, it basically just doesn't allow it to get a C2 capacity. And these are pretty reasonable things. We don't want anchors to displace a huge amount when we're using them. We're not accounting for that in design. But the actual impact on the end result is reasonably minimal. It's more of a pass-fail kind of thing with regards to displacement performance. Basically, when it's all said and done, that's where this C2 capacity comes from. There's a couple of vocabulary things that might be worth noting. You'll see in supplier documentation, or especially any European country that sells products in New Zealand, they'll be using the European language. We often call things capacities. The language you'll see published in documents from Europe will be resistance. Synonymous, really the same thing. The reduction factor, the strength reduction factor that gets applied in Europe is called a partial factor, and it's represented by a gamma. It varies depending on the kind of a couple of aspects, but often suppliers already applied it. And if that's already applied, you wouldn't then go and apply the New Zealand strength reduction factors on top of that. They try to achieve the same thing effectively. All right, that is basically where tension capacities come from, C2 capacities. Obviously, you do a similar sort of thing for shear. I'm not going to go into this in the same sort of detail, but it is exactly the same philosophy. You start with your base shear capacity, you have reduction factor, your alpha and beta reduction factors based on the impact of the different mechanisms. Now, one thing that is interesting with shear capacities is we don't run that cyclic crack test. And this is because someone did a really nifty study, which has probably saved hundreds of thousands, if not millions of dollars worldwide in anchor testing, that basically compared the impact of the cyclic shear test and the impact of the cyclic crack test on the shear performance of post-installed anchors, and basically found that the cyclic shear test was reliably more adverse. And so we're able to exclude one of these tests from the shear testing. Which means that the mechanisms that C1 and C2 are allowing for are actually the same. And with regards to shear capacities, the main difference is just that we're allowing for a larger crack width. And that does have a negative impact on anchor performance, obviously, but that really is the main difference between the two. And then that's actually the test you run for cyclic shear. You're bringing your anchor into negative and positive shear in both directions. And quite often you start, for some anchors, you start getting kind of steel failure governing, especially if you're deep embedment, which is a really positive failure mechanism with regards to anchor performance, rather than kind of pry out or anything like that. In general, it's even when you start putting seismic things into anchors, kind of shear performance is a pretty reliable mechanism, because at the end of the day, you've got a piece of steel in a substrate. Okay. That is, broadly speaking, where we are getting these capacities. Now, this next section, I have a number. I'm basically wanting to highlight a couple of things that I think designers should be aware of and thinking about when you're doing sorts of designs with these values. A bit of a caveat here. it's really easy to pick apart other people's work. And putting together these kind of test procedures would just be a monumental effort. The amount of research that is required, and even just the code development process, it's a huge amount of work. But it still is useful for us to highlight kind of where it doesn't fit what we do quite perfectly, so that designers like yourselves can understand what's going on and kind of can accommodate this a little bit better in design. And so this is some of the kind of ambiguities around these test procedures. Okay, the first one, crack widths. So I showed this image before when I was talking about where the crack widths came from. If anyone wants to really find lots of bedtime reading, you can go Google the Unified Crack Protocols, which is where all this comes from. But we have those kind of two crack widths that we care about if we're talking about C1 and C2 capacities, which is that 0.5 mil crack width and that 0.8 mil crack width. Now, I have not been able to find any published justification for the 0.5 mil crack width. I have talked to many people who are very knowledgeable in this area. I have looked myself, and for love nor money, we cannot understand where this 0.5 mil crack width comes from. Now, that's not to say it's wrong or misrepresentative, but I certainly don't, and nobody I know can really justify why we are using 0.5 mils rather than 0.6 or 0.4. And it's possible that it was just a judgment call based on kind of experience. Not sure, don't know, don't really know where it comes from. The thing to, I think, from a design point of view, to be aware of is that if you're using a C1 capacity or looking at a C1 capacity, fundamentally, you're allowing for a 0.5 mil wide crack maximum. If you are in a scenario where you're expecting cracks larger than that, your C1 capacity is not going to be very not going to be a very good representation of what's going on. If your cracks are smaller than that, your capacity is going to be a little bit conservative. So keeping that in mind, that when you're using C1 capacity, it's that 0.5 mil crack width. Now, there is published justification for where the 0.8 mil crack width for C2 capacities comes from. And that's where it's from a research study that I've got a screenshot from on the screen. I think I mentioned this at the beginning. It's basically looking at the elastic portion of a reinforced concrete beam, minimally reinforced, pretty standard size. You load it. When you start getting yielding in your reinforcing bars, they used predictive crack width equations to estimate that the crack width at that point would be 0.8 mils. Now, they had to pick something, but it is not immediately obvious to me how universal this 0.8 mils crack width is. If we have a really deep beam, a really heavily reinforced beam, it seems intuitive that those cracking behaviors are going to be different. The predictive formula they used were empirical formula that were developed on reinforced concrete beams in the elastic range. And so whether or not that kind of translates to the point of yield is not sure. The other aspect to this is that there's just a lot more than beams that we deal with. And so I thought I'd take a step back and maybe take everyone back to first year engineering school, where we have a building structure, and we can look at the different elements. So we have beams. Excellent, beams are good, very important. We also have not beams. That's not a beam. That is also not a beam. Still not a beam. Definitely also not a beam. And I'm being a little bit facetious, but I hope the point's got to come across. This 0.8 mil crack width apparently has been developed for reinforced concrete beams. It's not immediately obvious to me that that translates perfectly well to other elements in a reinforced concrete structure. Maybe it does. Not sure. From a design point of view, I think the really important thing to keep in mind is that if you're using a C2 capacity, what you actually are allowing for is a crack width up to 0.8 mils. If for whatever reason you're expecting cracks larger than that, the C2 capacity is probably not very appropriate. It's probably actually overrating the capacity. Similarly, if you're expecting cracks less than that, then your capacity is going to be quite conservative. And one of the reasons we started playing around in the lab, trying to figure out how sensitive things like crack widths were to the end result, is because we wanted to understand how much this matters. And it's really sensitive. Like the outcome really matters on what your crack width is. And so it's a really important thing as a designer to be aware of, that when you use these values, that is what you're allowing for. And that's what's been tested. And that's the testing that's behind the value that you're using. Next one. So the other parameter that I mentioned in that really critical crack cycling test that has a really big impact on the end result is the number of cycles we do at the largest crack width. So basically the number of 0.8 mil wide crack width cycles that we run has a really big impact on the end result. You can kind of imagine this, right? So if you're opening and closing a crack around an anchor, you're going to be crushing all this concrete around the anchor. You end up just turning things to debris. You do that enough times and your anchor is not going to be able to hold on to anything. There's going to be nothing left for it to hold on to. Now, when you start digging into where the number of cycles and things like this come from, I've mentioned a lot now that all this testing kind of comes out of California. Well, a lot of it comes out of California in the 2000s. Which in and of itself isn't a problem, but when they started looking at developing these crack protocols, they very rationally used their local seismicity. And so these were all developed based on a 90th percentile 475-year return period earthquake in LA, which equates to a 10% probability of exceedance in 50 years. That's all well and good, except there is no way for you to scale this when you're doing the testing to any other return period of earthquake. And there's definitely no way that I'm aware of, at least, in design for a designer to scale that for a longer design life or a shorter design life structure. And this can have some pretty meaningful impacts. It means that if we're dealing with a short design life structure and we might be realistically designing for kind of a shorter earthquake, our capacities probably have a little more conservatism in them. But if we're dealing with something like critical infrastructure, where we're really wanting to ensure that these anchors can handle a very long return period earthquake, there are scenarios where C2 capacities are actually probably under conservative. They probably overrate anchor capacities in certain scenarios. So I think that's really important to be aware of, because if you're someone designing critical infrastructure and you're doing lots of person-taught anchors, it's something you should think about. And there's ways to kind of protect yourself against it. You can build redundancy into your anchor design, but this isn't generally communicated in the one magic C2 value that you generally get for use in design. And just to kind of re-emphasize that point, this was put together by a guy called Dorian, the WSB research, concrete research lab down in Wellington. He's written a few papers on this in the last couple of years, if you really want to dive into some of the weeds on this. But he's gone here and compared the ULS design target and the maximum considered earthquake, which is part of the US codes, to kind of importance level 2 and importance level 4 response spectrums across New Zealand. And you can see that obviously it's range, right? It's not all one level of response spectrum. So that's kind of just something that's built in to how we testing these anchors and what we're doing in design. Next one. So say we have a scenario, and obviously there's many different scenarios in which this would come up, but I'm just using this as an example. Let's say we have a reinforced concrete frame building. We go in and we retrofit this for whatever reason. Say we want to bring the drifts down. We put in a big steel brace frame. We've designed it to be much stiffer than our existing kind of concrete frame, and so we're not really expecting the concrete to displace to the point where you're getting yielding in the reinforcing. We're expecting most of the lateral load to be carried by the steel. In this scenario, at what point are we getting 0.8 mil cracks which are associated with the yielding of our reinforcing in our reinforced concrete structure? The reality is we're probably not within the scenarios that we're designing for. And this isn't necessarily a problem so much. Like it's conservative, put in some more anchors, not the end of the world in this scenario. But it's quite good to be aware that if you've got smaller crack widths, that magic 0.8 mil number, you've got some conservatism in your anchors, put them up to 100% utilization, you can sleep very well at night. So just understanding where you sit in terms of how much conservatism is there, I think is quite beneficial from a design point of view. The next one that's also pretty clear cut. all of this, everything around kind of C2 capacities, C1 capacities, really everything in this space is all focused, understandably, on reinforced concrete. And if you think back to that kind of image I showed, which was the basis for the fundamental assumption that we are designing anchors to allow for the fact that when cracking occurs in concrete, it happens where the anchor is. That's really important in reinforced concrete. We have to get cracking in reinforced concrete for it to behave as we designed. You need that reinforcing to be engaged. Things like pre-stressed concrete are an entirely different mechanism. For pre-stressed concrete, you're relying on compression from the pre-stressed strands, or if you post-tension a reinforced concrete section, this might be the same. You're relying on compression across the cross-section to resist those loads. You're not relying on cracking to enable engagement of reinforcing and yielding of steel. And so because we don't expect the same kind of cracking behavior, C2 capacities or C1 capacities perhaps don't really represent the scenario very well. And where we are getting crack widths less than what is used in the testing, the capacities we use are going to be very conservative. And so if you're putting stuff into pre-stressed beams and you're just doing a connection, and because 301 tells you to use a C2 capacity, and if you're just a little bit handcuffed by that, which in most scenarios in New Zealand kind of are at the moment, at the very least, know that you have a lot of redundancy in that anchor, and you can put that up to a really high utilization, and it won't be an issue. Some exceptions there. Obviously, all of these are generalizations. You obviously can get cracking in pre-stressed elements, and anyone who's looked at any of the recast floors team, pretty impressive work over the last couple of years. If you're looking at hollow core units or any kind of pre-stressed unit, and you're dealing with the edges, especially from an alpha unit, you're going to get pretty significant cracking in those areas. So it's not that they never crack, but in many cases, we're dealing with a different system to reinforced concrete. Okay, this one. Now, there are a range of different kind of applications where this happens. This one is one we're quite familiar with because Python is a hollow core anchor, and so this is one we come across quite often. But there are other scenarios where you get this effect happening. What I've got there on the left is a comparison in the load resisting mechanisms between a post-installed anchor and a through bolt connection. We obviously don't use C2 capacities for through bolts. It's not a post-installed anchor. And you can look at that little sketch there for tension loading. And you can see when we load it in tension, what we actually have is a bearing connection, right? It's a plate on the top that's bearing on the top. It's a bearing connection. It's not a post-installed connection. C2 capacities don't mean anything. And similarly, if we look at the shear mechanism, right, we're loading that from the underside of the slab. Your shear mechanism is a bearing connection between the steel shank of the rod and the concrete underneath the core. If we look at the post-installed anchor in this scenario, if we look at the tension connection, that really is a post-installed connection. You've got a post-installed connection between the thread, if you're using a screw anchor, or the epoxy if you're using an epoxy anchor, and the concrete. And so 30101 tells us to use a C2 capacity there. We know in the back of our minds, it's probably a little bit conservative if it's in kind of the middle of a pre-stressed unit. We're not expecting a lot of cracking, but kind of codes tell us we have to use a C2 capacity. But the shear loading scenario is a little bit different. And this is for where we have an offset between what is the post-installed connection and the point of shear resistance. When we load one of these anchors from underneath the hollow core unit, the actual load resisting mechanism is exactly the same as the through bolt, right? We've got a steel shank, we're bearing that against concrete. It's a bearing connection, that's not a post-installed connection. The C2 shear capacities have nothing to tell us about how that's going to perform. And so when every now and again, you do come across a scenario where your anchor and shear is actually behaving as a bearing mechanism and not as a post-installed connection. One thing to really highlight so this doesn't get misinterpreted, if you had a solid piece of material and you went into the solid piece of material, that would be a post-installed connection in shear because you're going to get that cracking occurring around that, that post-installed connection area. Okay. A little bit on codes and standards. So most countries, definitely New Zealand, I think probably all codes and standards around the world, at least all the major countries, they are built in a hierarchy. So we have kind of our building act, the building code, then we have our kind of standards, and the standards are in a hierarchy. We have our loading standards, our material standards, and our specific design application standards. Because they're in a hierarchy, whenever there's a disagreement between any codes, whichever code is above the other in the hierarchy, it takes precedence. And there is a little bit of confusion I've come across in some of the specific design codes that we have in New Zealand. The three I've got down the bottom are fire hydrants, engineering systems, and automatic fire sprinkler systems. I believe there are bits in those codes where you could reasonably read it and interpret that the appropriate thing to do is use a C1 capacity. Technically, from purely a code compliance point of view, because these are all specific design standards, they're all subservient to 3.101. And because it is a reference in 3.101 that's causing us to use C2 capacities, technically that overrules anything that is in those specific design standards. That's not a comment on anything other than technical code compliance. So if you're doing a verification method, technically that's the way our codes are structured. One other one that I do want to highlight, this is a more recent one. This got published through brands, but it's ER95's Code of Practice for Sizing Performance of Non-Structural Elements. I've not been involved in this at all. My knowledge of this comes from just reading it. So if you are doing design of non-structural elements, I suggest go read this for yourself. But my understanding is it's come from trying to alleviate some of the pain in the industry. You do have scenarios where people just don't have C2 rated anchors for specific things, especially small diameter anchors and shallow embedments. It's a really hard thing to make work through a C2 test program. And so I think this has been a little bit of the industry's response to that, to try and alleviate some of that pain and perhaps take more of a risk appropriate approach. I suggest you go read it for yourself and be aware of it on the first hand, rather than taking anything I say here as gospel, because again, I'm not privy to the background behind it. But there are two interesting concepts that I want to highlight that are in it. It refers to some scenarios as low risk, what that appears, and then that being the justification to use a C1 capacity over a C2 capacity. What that appears to reference is basically just kind of lightweight non-structural elements, that the risk of anchor failure is pretty minimal. It's not going to be a huge deal if that comes down. And the other one is the concept of redundancy. I think this is a really interesting concept to be familiar with, because it is relevant, and it's one of the ways where you can, if you're concerned about anchors, really improve the likely performance of the system. In the context of this document, they say where you've got redundancy, that's also lower risk, and so that might be justification to use C1 capacity. But the concept in general, and this is accounted for in some material design standards, where basically in a load sharing factor that improves your performance slightly. To the best of my knowledge, not included in the anchor design standard, but it is a real mechanism. The idea is basically that because we use 5th percentile capacities, that's based off the idea that we're designing a single element. So if we have single anchor and you get a normal distribution of possible performance, we use a 5th percentile capacity, and then we downrate a little bit more. But that's to account for 95% of the time that angle of more capacity than we're designing it for. As we load share between more anchors, our likely capacity, or the appropriate capacity used, tends towards the average. So as the number of anchors tends towards infinity, the capacity of the anchors in aggregate tends towards the average. Basically, because the way we design it is just with 5th percentile capacities, as we add more redundancy, as we load share between more anchors, we are getting inherent statistical conservatism built into the system that we're not allowing for. And so I think that is an interesting concept to be aware of, both from this document's point of view, but also more generally, just in kind of good practice design. You are getting pretty meaningful improvements just by adding redundancy in terms of your anchor design. Okay, if I was to kind of summarize all of that with the question that is the title of this presentation, which is, what is a C2 capacity? I think a reasonably precise answer would be that a C2 capacity is the expected 5th percentile capacity of a post-installed anchor in a reinforced concrete beam just outside of the plastic hinge zone in a crack that is 0.8 mils wide in a 90th percentile 475-year return period earthquake in Los Angeles, which is quite a specific thing. We're obviously not just using it for that scenario, but I think being aware of what specifically that value really represents is useful and can be kind of accounted for a little bit in design to adjust how you're using and how you're designing with post-installed anchors. Now, a comment more broadly on this. This really isn't a stagnant part of our industry. This really is ongoing. There is a lot of drama going on in the US industry, as you might expect, with the most recent updates to ACI 355. There is a little bit of a movement by some people to try and dial back the degree of change here to try and go towards a scaled system for various reasons. I suspect they won't have much success just because of how the process works rather than anything else. And so I really expect that that will proceed as written, and that when that next code change comes into effect, which I think is next year, possibly 27, but next 26 or 27, the US will be only using C2 capacities. But there's obviously a lot of work in this space for the industry as a whole to kind of improve what we're doing, clearly. And it is, while it is a relatively small part perhaps of what most designers think about on a day-to-day business basis, it can have a pretty big impact on the job as a whole. And so I'll leave you with a kind of a final comment that I think is important for us to keep in mind. It is the case that because many of the individuals who know the most about anchors know this because they work with anchors, but everything that gets published in the industry really should be angled towards giving the designers what they need to A, understand what they're using, and B, giving them the information they need to achieve the design intent. And it's really important that when we're building assessment criteria, that they exist to support the designer in that goal, rather than helping suppliers differentiate products. And so I think it is something that we just have to keep in front of mind and see it as the role of industry organizations like Engineering New Zealand, CSOC, NZSCE to kind of promote this on behalf of designers. That is it. I thank you all for your time. Hopefully some useful information has come out of that for you, and hopefully that will be somewhat useful in design going forward. And I think we do have a bit of time for questions.
Robert, that was absolutely wonderful. We have 14 questions in 6 minutes. just saying, you know, okay. So we're going to try and get through actually 15 questions. We'll get through as many as we can, everyone. Okay. I hope Robert's happy with that. Daniel asks, thanks for clarifying the use of EOTA TR045 and the ETAG 001. Although I agree that Eurocode 2 Part 4 is the state of the art and ETAG 001 is superseded, using anything different to that than what is stated in 3101 would be an alternative solution. That's more of a more of a statement than a question, but I guess he's true.
Technically true. Technically true.
Good answer. Okay.
Practically speaking, it's an alternative solution, but generally that's what's done, and that's kind of the more appropriate thing to do.
Which I think is fine as long as it's well documented in the calcs that it is. So, Steve asks, would the use of fiber reinforced concrete affect the capacity of anchors compared to standard reinforced concrete, allowing the same crack widths? Interesting question.
Almost certainly yes. I don't know enough about the crack behavior of fiber reinforced concrete to tell you in what way, but the thing to be aware of is just the crack widths, right? The thing you're thinking about is those crack widths. So whatever ability we have to predict crack widths in fiber reinforced concrete, which is not something I've looked into, but if we're getting cracks bigger than we would in reinforced concrete, then the impact's going to be more significant. If they're smaller, less significant. Not sure is the honest answer on that, but it would almost certainly impact it one way or the other.
But like you said, it seems to be quite a changing industry that you're in, so that might become, the answer might become obvious in future years, perhaps.
Hopefully.
Okay. My friend Anonymous asks, in the case of strengthening an existing reinforced concrete wall, but mu equals 3, ductile deformation is expected, how should we consider plastic hinge with C2 capacity? Is it common that anchoring some steel plates or angles to strengthen the wall to slab junction?
Say that again. The last portion of that again. I missed a couple of those words.
Yeah, I think
We're
so.
looking at
In the case of strengthening an existing reinforced concrete wall, but mu equals 3, ductile deformation is expected.
Yep.
How should we consider plastic hinge with C2 capacity? Okay. It is common that anchoring some steel plates or angles to strengthen the wall. I think what he
into the
means.
plastic hinge zone.
Yeah, I think that's what
Yeah,
it is.
you're not going to be getting good performance of anchors in a plastic hinge zone. Especially with the thing. As a general rule, you want to be using mu of kind of like 1 to design your anchors technically, but yeah, you just really we shouldn't be putting anchors into plastic hinge zones as a rule, and it's absolutely a C2 capacity doesn't cover that.
I think that's pretty clear. This is quite a long question. Post-installed anchors are often used for pipe supports and other minor structures fixed on top of concrete foundation pads or slabs. As stated, C2 is mostly unavoidable in New Zealand, but the foundation pads are almost always sized for stability. The reinforcement may be very lightly loaded even at ULS seismic, so cracking is going to be minimal. Is it reasonable to use C1 in this case?
So there's 2 sides to this. There's the engineering side and the kind of code compliance side. Like from the engineering side, yeah, if you've got a deformation controlled, massive, thick slab that isn't going to crack in a reasonable scenario, your C2 capacities are wildly conservative. And a C1 capacity, if you can show your cracks are below 0.5 mils, is probably more appropriate. Code compliance point of view, different thing. That will have to be an alternative solution. So you're going to have to justify that. And in my mind, the way to justify that is to show beyond any reasonable doubt that your cracks are really, really, really small.
There's sort of a follow-up to that one too. I suppose, and this is the same question, I suppose this would be an alternative solution, but at this point, it seems that every use of post-installed anchors is an alternative solution. Any comment?
Yeah, well, be thankful that we have the alternative solution in New Zealand. So the US doesn't have this pathway. It's really hard to do an alternate solution in the US, and they basically have to be compliant with the code. And so we're actually quite fortunate in New Zealand to have this well-established alternative solution.
It's a wonderful thing. Okay. Next question: when specifying fixings and seismic resisting systems, but we know there will be no cracking, i.e. concrete is in compression, do we still need to use C2 capacity? Answer's no.
Well, again, it's that duality that we're stuck with, right? So like the codes say yes. Codes don't care what's going on. It's just the seismicity of the area and the importance level of the area.
I see.
Code says yes. In most scenarios, many scenarios, it might just be easier to follow the code, but like we have the alternate pathway, there are efforts.
Yeah, okay.
I've seen it done. You can go through it can be done that you prove beyond reasonable doubt that like it's more appropriate to use that. And kind of this is the basis for that document I showed in one of the last slides, right? Is trying to alleviate some of these kind of really low risk scenarios.
It all comes down to determining your crack widths, I guess.
Which is and a note on that, that's really hard. Our formula that we use for crack width estimations aren't very good. And so you do need to be careful. You really want it to be beyond reasonable doubt before you start doing that. Because like we get frustrated with the capacities being low, but they do represent a real thing that can really happen. If you are getting cyclic crack behavior around an anchor, the impact is real. And so, yeah, there's an unfortunate amount of nuance that we have to play with here.
That's always the way, I'm afraid. That's life. Thanks for the presentation. Do you have any thoughts on C2 compliance for post-installed, i.e. epoxy anchors with a standoff arrangement?
I'm not sure if I follow the significance of the question. You would need a As in, like the significance of the standoff to the.
I imagine that's the. I think that's the question.
It
But,
doesn't really. I can't imagine it really makes a difference.
okay, I'm not sure about the question. Sorry, anonymous. But so we'll move on. Ismail, as most structures are IL2 and therefore require C2, the presence of cracks becomes critical. This is
Of what a C2 capacity is.
This is reasonably particularly in concrete frames, beams, or walls. However, but now I've lost it. How should we approach anchoring into foundations? Is there any way to justify the use of C1 instead? We sort of touched on that before.
Same issue. You've got what our code says, which is pretty rigid, and perhaps in many applications like this, it's not a great representation of the reality that we're experiencing.
No, that question person goes on and makes a little interesting comment. Actually, we frequently design post-installed anchors into foundations for portal frames, SED timber walls, and once C2 is selected, the capacity of most post-installed anchors becomes significantly limited. True. For example, in a residential construction, a jib handy bracket with M10 anchor screws is rated for 15 kN characteristic load. However, when the same screw is designed under C2 requirements, the capacity becomes negligible. I'm sure it does. Yeah, interesting, isn't it? Yeah. That's not really a question.
It's really interesting actually watching the test, because that cyclic crack behavior just decimates the concrete around the anchor. And so once you see one of those tests, you're like, I understand why these capacities are low.
Yeah, really, probably very relevant in the case of a bottom plate fixing to a slab, because it's going to be right next to the edge of the slab too. So anyway, if we are designing a structure or member for mu equals 1.25, can we design using C1 anchor despite the region?
Unless I misinterpret the question, no.
No.
Nothing to do with the only thing that defines it in our code is the importance level of the building and the seismicity of the area.
Done. It's pretty right. Okay, a couple more. We've got, oh God, there's still ones to go for. When cast-in anchors are used, the C1 and C2 seismic categorization does not apply.
Correct.
And the design is carried out with standard anchor theory. Done. However, if we start installing post-installed anchors, the capacities drop significantly. Oh, I've lost the question. Sorry, I bumped the mouse. The capacities drop significantly. Is this what happens in reality, or is it just a bit too much conservatism about post-installed anchors? I think you explained that pretty well, actually.
So our codes don't do a good. So that basically it's that cyclic crack mechanism. That's the reason why we have such low post-installed anchor capacities for C2 capacities. The honest answer is we're just not allowing for that when we do cast-in design. It's going to be less stress raised because we are embedding it, so it is better. And the second you have a hook or anything on your cast-in item, then it's pretty resilient against that cracking mechanism, because you don't care if it crushes a little bit around the angle. You can into the concrete. But hypothetically, if you just had like a straight bar that was just cast into the concrete, and you got the crack where the cast-in bar was, and you got that cyclic behavior, it's possible that our designs for cast-in anchors are not very good in that sense.
Yes.
But normally you have a hook or something, and then that mechanism is not such a big deal.
Okay. It does not seem that longitudinal or shear reinforcement is taken into consideration in C2 rated anchors. Does the presence of rebar improve the seismic performance similar to cast-in anchors?
Yeah, it would, and no, it's not taken into account. Because the other thing that it isn't taken into account is the embedment depth. Because if you think about a reinforced concrete beam, we're talking about crack width at the surface. But when you do the test, you crack the entire slab and your entire slab moves in and out. But in reality, you're getting a triangular crack, right? And the deeper you go in, the less cracked it is, or at least the thinner the crack is. So you're also getting some conservatism if you have really deep anchors and you're in a beam and you're even all the way up in the compression zone. Doesn't get taken into account in the C2 test. Yeah.
Okay, just skimming through a few questions. I'll give it three more. Some of the questions that are coming up, or that we still have to answer have pretty similar to previous ones, so I won't go there. But one is a certain anchor manufacturer's anchor design software demonstrates anchor capacity to there being a gap between the anchor and the base plate hole. What is your recommendation about this?
I think I'm reading between the lines, but I think we're talking about grouting. Like if you have a steel plate and you have a hole and you're using, it's typically an epoxy anchor, and you go all the way through and you have a slight slop between the anchor and the hole, and you can grout that and get better results, or use like a steel plate. It takes out basically the slop and shear. I think that's what we're talking about. It's a pretty real mechanism. I believe it's just a factor that you apply in the C2 test program. It's just a factor if you want to take advantage of that as a manufacturer, because someone did a study and worked out the kind of reduction you get from that slop. I believe that that's where that comes from. So that's a relatively easy thing for a manufacturer to provide.
Okay, a couple more. Jump to the last question first. Do Python fixings have anchor design software for New Zealand?
We do not have anchor design software. No,
Okay.
we're old school. We have tables.
Oh, you got tables instead. Cool. Look, I think there's a question about bolting. Should we bolt through plastic hinge joints?
Yeah, or through bolts would be a good option if you're going into a plastic hinge zone, all the way through at a bearing plate on the other end, pretty resilient. Yeah.
Okay. What do you suggest for post-installed anchors so that they can reuse a foundation for an IL4 asset in Wellington? Should I mention we prefer a standoff detail for corrosion reasons? Post-installed anchors. That's a pretty broad question, isn't it?
Can you just repeat the question?
What do you suggest for post-installed anchors so that a foundation can be reused for an IL4 asset, importance level 4 asset in Wellington?
Okay, I'm going to assume that this is with regards to the capacity, specifically with regards to the number of cycles we're allowing for in long return period earthquakes. My contact details on the screen, so you can feel free to reach out if you do have any other questions that we don't get to.
Okay, I think that's...
With respect to that, I suggest redundancy. Whenever you're dealing with these really long design life, high importance level buildings, putting more anchors in has a more advantageous effect than we calculate. And that's because of the effect of redundancy. So your likely capacity actually tends towards the average rather than the 5th percentile that we use. And so that redundancy is a really good way to build in additional capacity that we don't actually calculate.
Right. Okay, look, there's a few questions still to go, and I'm sorry to those people whose questions we haven't answered. I'll take a note of them. Robert, okay, if I send them through to you, maybe we can...
Yeah, shoot them through.
You can give us a brief answer and then we can publish them on our website. I hope that's okay with everybody. Otherwise, it's 1:10, and I know that people are probably haven't had their lunch yet, or and that sort of thing. So I will really, Robert, that was bloody wonderful.
Thank you.
I found it to be great. Better than I thought it was going to be, actually. Sorry, I meant that in a really, really nice way. But our audience approached over, nearly 300 people. So obviously it's a topic that generates a bit of interest. So, we might have hit the nail on the head with this one. So huge thanks to you and a huge thank to Python Fixings. Okay. So
you're welcome.
Thank you so much. And to everyone else, this is our last technical webinar for 2026. But as part of the current elections, there's an online Meet the Candidates opportunity on the 19th of November at 12 noon. So, and this a couple of weeks later, there'll be a Meet the New committee online. So, please come along and ask questions, but not any tricky ones. And 2026, our webinar series, we're going to keep it going. And if you've got any suggestions of things you'd like to talk about or know about or learn about or contribute about, please go on to the egpnz.org website and let us know through the contact tab, okay? And so thanks everyone, and thanks to Robert. We're in Seattle. I understand it's only 12 degrees at present, so I'm sitting here in Hawke's Bay. It's 27. And so thanks so much, Robert. I'll hand it back to Megan to end the webinar. Thank you, everybody.
Appreciate it.
Thank you.